is equal to, and just write this down for a second. Don't even ask me what that is. Just write that down. So this means this, and this means that. So at the end of the day, what the evaluation theorem says is that if you want to find the area under F between A and B, then what you need to do is find its antiderivative and then evaluate the antiderivative at the right endpoint of the interval and subtract from that the antiderivative at the left point of the interval. If you can do that, you'll have the area. All right? Now, I told you to ignore this. Just let's do an example, and you'll see why that piece is there. Okay? So here it is. Example. Find area under f of x equals x squared minus 1 on the interval 1, 3. What's the answer? 20/3, right? But let's see how we can get that without the Riemann sums, right? That's the same problem we just did. So now what we'll do is we will say, all right, well, what this is saying is they want us to do this, but instead of that, they want the actual area, so we have to put the limits of integration on there, the 1 and the 3. Okay? Questions? The next step is to write this down. I told you to ignore it, but let's see what this really is. This gives you an opportunity in your work, as you're writing, to actually write the antiderivative down. And then this is just going to remind us that we still need to plug in the two endpoints to get our numerical answer. So I'm just going to write my antiderivative down right here. 1/3 x cubed minus x, right? That's my antiderivative. Now I should put plus c here. However, because I'm going to do this minus this, I'll have a c in this one, won't I? Yeah. And I'll have a c in this one. And they're going to cancel each other out. So you do not need to put your c here, because it's going to go away anyway. So I'm going to put a bar here next to this, 1 down here, and 3 up here. So do you see how this is just kind of like a placeholder for you? An opportunity for you to write the antiderivative down and have it there sitting in front of you? And now the next step would be to plug the 3 in, right, because 3 is the b. Plug 3 in, and then once you get that answer, subtract from it the 1 being plugged in. See that? So I like to do it this way. I like to write 2 sets of parentheses. One of them, this is going to be for my f of b, and this one's going to be for my f of a, and then I'll subtract the 2. All right, so let's plug in 3. Plug in 3 into here. We get 1/3 times 3 cubed is 27 minus 3. So that's 3 being plugged into this, right? Now plug in 1. So you get 1/3 times 1 cubed is 1, so minus 1. So that, right? What's 27 over 3? 9. 9 minus 3? 6. So I have 6. And then over here, I have, well, we'll put these two together. What's that? 1/3 minus 1 is negative 2/3. And so I'm going to go, this will be minus, but then minus again, so plus. So plus 2/3. And if you get a common denominator there, you're going to get 20/3. So that is not a coincidence. That is the power of the fundamental theorem of calculus at play there. I remember I have a little story that goes with the fundamental theorem of calculus. And when you get to Cal 2, you'll hear this a little more. There's a fundamental theorem of calculus, but there's multiple versions of it. It's kind of like different ways you can look at the theorem. This is kind of like the end-all result that we use all the time. Like this. I guess I'm just trying to prepare you for other versions that you'll see in Cal 2 first, but when it comes down to it, when you actually start doing all the work in the class, you're going to be using the evaluation theorem practically the entire time. So anyway, the story. When I was in school, I don't remember what level I was at, but I was already a math major, and when you're a math major, you have to go back and you have to go to like calculus, and you have to prove all the theorems that you use. So like the fundamental theorem of calculus, you have to be able to prove it. And I remember I was working on the proof for the fundamental theorem of calculus for a couple of days, and I couldn't figure it out. And we didn't have the internet where you could just go watch someone prove it, you know? You actually had to figure it out. Yeah, it was tough. And anyway, so I mean, that's part, if you're a math major, that's the whole thing though. It's weird for math majors these days because there's so much information out there that you can kind of like find the answers, but part of being a math major is figuring it out on your own.
It's the question,
Yeah.
it's the questioning and the logic.
Yeah, we used to have a rule, like, because as a math major I had to tutor in the math lab at the university, so that was kind of weird because you'd be in a tutoring lab and people could walk in with any question from like anything, engineering, you know, physics, and you had to be able to do the math, and it was, that's pretty intimidating, right? But we used to have a rule in that lab that if a math major came in and they asked for help with a theorem, to prove a theorem, that we weren't going to help them. It's like, that's the whole point, is that you need to be able to do this without help. So anyway, I was trying to do this without help and to prove the theorem. And I had a dream, and in the dream, this is the first time it ever happened, in the dream I actually was able to figure it out. But it was only because I had been thinking about it so much that when I was dreaming I was still thinking about it. And that wasn't the first time that happened. That happened several times in my academic career where I actually dreamt the solution. It's weird. But so I got that missing piece, and I got up and I wrote it down on a whiteboard, and I was like, I got it, you know, like I had it. And I was so proud of myself. I went to go visit my parents that next day or something. I took my whiteboard with me, and I had it in the back of, I had like an SUV, so it had like this little thing that popped up, and I had it back there, and I was like, Dad, you got to come check this out. And my dad didn't care, but he was, all right, whatever you're happy about, son. So I went out there, I opened, well, they had a dog. They had a big old fluffy white dog, and he thought we were going to the park. So he comes running out and jumps up in the back of my truck and is like sitting there wagging his tail, erasing all my proof. And anyway, I knew the proof. By then, I mean, I knew it. I could reproduce it, okay? But I was just like, well, that was my proof that I wanted to show you. The dog was all ready to go. Anyway, all that dream wiped away. All right. Pretty nice, huh? This is pretty nice, the evaluation theorem. It's definitely gonna make our lives a lot easier. So let's do a couple of evaluation theorem problems. I want you to find the areas under some curves, and we're gonna run into some interesting things here. I'm not sure if you've ever been sitting there, maybe in pre-cal. Maybe you were thinking this. So here's an example. Do you remember in pre-cal the function sine x? Sine x looked like this. And it went both directions, right? Were you ever curious what the area of one of those little arcs was? Nah, probably not, right?
Does it change with, like, you know, when the amplitude change continuously?
Well, just for this function though, sine x. For sine x, what's the area of that little arc? Curious. Could we figure it out?
Sure we can.
Yeah, we can now.
Let's go.
So we need to find our limits. Where are we starting and where are we stopping? So this is 0. This right here is the 2 pi, so halfway would be pi, right? So I need to do this integral sign. I need my limits of integration to go from 0 to pi, right? And I need to put in here the function I'm going to integrate, which is sine x. And then that little dx is our little placeholder. It's just going to keep us, you'll see if I have a little time today, I'll show you how important that dx is. All right, that's it. So now you need to come up with the antiderivative of sine. negative cosine. Now be careful with that, remember, because it's antiderivative, you have to keep track of that negative sign. So the antiderivative of sine x is negative cosine x, and then I'm going to put my little bar here, put 0 and pi here. So are you kind of catching on with how this is just kind of like a placeholder, an opportunity for you to just write things down and keep things in order? Okay. And now I'm going to do my two little subtractions here. And I first plug in pi. So I'm going to have negative cosine of pi. And then plug in 0 will be negative cosine of 0. What is cosine of pi? Cosine of pi. Cosine of pi. It's the x coordinate at pi, so that's negative 1, but then minus, so 1. 1 minus, okay, cosine of 0 is 1, but then negative, so that's negative 1 also, right? Or negative 1 here. So this turns out to be 1 plus 1, it's 2. Is that not awkward? Does that not seem weird that the area under that curve is a nice integer?
Yeah.
It seems like you wouldn't think that the area of that would be 2, but it is. Questions? Yeah, this right here is called that's called one arc of sine, not arc sine, but this is one arc of the sine function. And the area of an arc of the sine function is 2. Okay? What would happen if I, instead of going from 0 to pi, I go to 0 to 2 pi? Do you think I'm going to get an answer of 4, or do you think I'm going to get an answer of 0? 0? So do we agree that if I do that, I'm trying to find the area between the function and the x-axis, that this blue area is either going to be counted as positive or negative? But how can it be negative? Area is not negative.
Yeah.
But think about how we calculated it. With the Riemann sums, weren't these little rectangles, wouldn't they be down here?
Yep.
And aren't the heights of the rectangles the function's value?
Yep.
And wouldn't the function's value here be negative?
Yep.
So wouldn't it be counting each area as negative? I'm thinking it's going to be 0. Let's see. Let's change it. It's very simple to change. Just change that to 2 pi. Right? 2 pi here. Change this to 2 pi here. And change that one to 2 pi, right? Isn't that the only thing that changes? So what is cosine of 2 pi? We're back at 1, right? So this is 1, but then negative. So that's negative 1. And now we get negative 1 plus 1. This is now going to be 0. So, this is a little bit troubling, because what this does whenever we're doing this evaluation theorem is if our graph goes below the x-axis, it's going to count it as negative area. So if you get an answer of 0, that doesn't mean that the function was flat the whole time at 0. It means that there might have been some positive area and some negative area, right?
They cancel each other out.
That cancel each other out. So this can become problematic if you're trying to find, let's say you have a polynomial that does something like that, and you're trying to maybe find the area between here and here. You're going to have some areas that are counted positive, some are negative. And so later on, Cal 2, you might have to find these x-intercepts and break it up into separate little pieces, and that's later, okay? I'm just...
So, but then you just change them to positives once you
That's right.
the x's, and then
Yep.
you're able to add total area.
That's right. So you get like a total area by breaking it up and then counting the negatives as positives, and like almost like an absolute value, if you want. Just take all the little integrals and then just take their absolute values, add them all up, and that'll give you like a total area. Okay. Well, I think I've established what I wanted to establish with, I think I've made it clear that the Riemann sums are nasty, but I hope that I was able to illustrate like where they came from, like why they were created. And then from there, the power of the fundamental theorem of calculus, because now you can find areas under curves without the Riemann sums. I know that there are some calculus classes. A lot of universities still do it this way, where you have to compute Riemann sums, like you have to just grind them out. I'm not going to ask you to do any Riemann sums. But I wanted to expose you to them. All right. Maybe I'll offer a take-home bonus or something like that. Yes? Yes? See, the thing is, I can only ask you to integrate certain things with Riemann sums. I can only ask you to do something that's either linear, quadratic, or cubic. Because the three formulas I gave you, like the Gauss formula, for the sum of the first n, or the sum of the squares, or the cubes, I stopped at cubed, right? So if I give you anything past a cubic, you won't have a formula at the end to break it down with. Now you have Google, so you could go find formulas, but
Are you saying go out and find the answer on your own?
I'm saying you could find the formula for the sums. All right. So we can handle finding the antiderivatives of powers of x, and we can find antiderivatives of things that we recognize, like the antiderivative of sine, right? But what about this? What if we try and find the antiderivative of I want to see what someone would do here. If I asked you to find the antiderivative. So I'm not doing the area. I should make this clear. That's versus. Okay, just so you make sure we can distinguish these. This is called an indefinite integral. And this is called a definite integral. The way you can remember the difference between these is this gives you the antiderivative and then plus c, right? You have this big family of functions. It could be an infinite number of functions. You aren't quite sure which one, they all work. So you're not really definite about the answer. You're within a constant. This is the area under a curve, and that is a definite numerical answer. And so this is called the definite integral. This is called the indefinite integral. This is an indefinite integral, right? So I want capital F of x plus c here. Anyone have an approach to do this one? Like do 4x plus 1 times itself, right? So this is, don't do this, but this is what we could do here, right? 4x plus 1 times 4x plus 1, and then we could do that, and you get 16x squared plus 8x plus 1, right? And then you could do power rule on each one of those. Is that safe to say? So that would be a way to do that? Okay. Let's change it. That's too easy then. Let's raise it to the 200th power. So I'm forcing you to not want to do this now, right? Unless you want that as a bonus question? No. No. I would never give that as a bonus. That's torture. Can we do this? I mean, we can't expand it, right? We don't want to do that. So maybe there's another way to do this. Maybe there's some technique. I'm sure that over the history of humans trying to find antiderivatives, that we had to have come up with some clever ways of attacking these things, right? You would think we had to come up with some methods to help us with these. All right, so there's several methods, and the only method I'm going to show you in here, because we only have one day left of class, is what's called basic U substitution. Basic U substitution. Sometimes people call it U sub. I like to call it U sub. U sub. But it is the first technique for finding antiderivatives that you learn. It's the first one. There is U substitution, integration by parts, trig integrals, trigonometric substitutions, partial fraction decomposition. Those are the 5 methods you'll learn in Calculus 2. All right? This is the first one. So you're going to have, if you take Cal 2, you're going to have some exposure to U substitution, which is good. There will be some overlap in your class. All right, so here's the idea behind U substitution. Let me show it to you first. All right, let me just kind of walk through it, and then I'll give you like more formal steps. What you're doing is you're looking at the problem, and you're trying to look for something in the problem. When I say something like some chunk of stuff in here, that when you take it, you imagine taking its derivative in your head. So I'm looking right now at the 4x plus 1. What's its derivative? What's derivative of 4x plus 1? Oh, no, derivative, not antiderivative, derivative. 4, right? So I'm looking for something. I see it, 4x plus 1. And now I take its derivative, which is just 4. And now I ask myself, do I see 4 anywhere else? So I can't look here because I already took that out, right? Do I see a 4 anywhere? Well, up here, yes, but do you see 4 by itself, like down here being multiplied through? No? Okay, so with the method of substitution, you look for something, you take its derivative, and then you go looking for that in there. You are allowed to be off by a constant when you're looking for its derivative. Let me just push this, hold on. I'm going to make a substitution, u is equal to 4x plus 1, all right? Now, when I take the derivative of this, I get du dx, I'm using Leibniz notation, is 4. The derivative of u with respect to x is du dx. The derivative of 4x with respect to x is 4. The derivative of 1 is 0. Agreed? So I said I could be off by a constant. What the hell am I talking about? Just follow me here. Do you agree with that step? Take this, multiply both sides by dx. Okay? Yes? So what I'm going to do now, it's almost like you're going to play this little like matching game. You see this 4x plus 1. I'm going to replace that in the problem with u, right? That is going to be replaced with u. Now, I'm going to try and replace dx with something. And here, I have something that has dx in it. Do you see the dx right here? Now, I don't have the 4, right? I didn't have a 4 up here. But this, because it's a constant, can't I just multiply both sides of this little equation by 1/4? Just scale it out. And wouldn't I have a new little equation here with dx there? Now, u substitution, the idea is that you're going to take the variable that you had in here and you're going to switch it to a new variable. You're going to make a substitution. The substitution we're making is to replace all 4x plus 1s with u. And we're also going to substitute my dx, and I'm going to replace it with 1/4 du. And I'm going to rewrite the problem. So what would this problem be if I rewrote it? I'd have an integral sign there, and then 4x plus 1 to the 200 is really going to be u to the 200 times, this is multiplication, dx, which is 1/4 du. Now notice I've rewritten the problem. Everything is in terms of u now, right? There's no x's in there anymore? Do you all agree? And then I could rewrite that as 1/4 u to the 200 du. Now what is u to the 200th power? Ignore the 1/4. What is the antiderivative of u to the 200th? 1/201 u to the 201, right? See, notice how I've changed this ugly expression that had to be expanded out into a nice expression in u, just u to a power? So let's do it. Let's actually take that antiderivative. This will be equal to, I have the 1/4 there. You said it'd be 1/201 u to the 201 plus some constant. So I'm just using the power rule there, just your basic power rule. And what do you think my last step is? Get u back to what it was, right? I mean, you got to get everything back to x. So u was 4x plus 1. So I'm going to rewrite this as 1/804 4x plus 1 to the 201 plus c. That should be my antiderivative. You see where I got the 804, right? Okay. How could we check our answer? Take the derivative. So if I took the derivative of this, I'd have to do chain rule, wouldn't I? I'd bring the 201 out, and when I did that, it would reduce, that would become a 1/4. Then I would have this raised to what power? 200. Then times the derivative of what's inside, which is 4, and that 1/4 and the 4 would go away, and you would just have this. Do you see how this like actually kind of took care of and compensated for the chain rule? We need to do another one. I'll make this one a little easier to see it. All right. So I'm trying to find the indefinite integral here. What is the antiderivative of that function? Can you split this into two fractions? Can you do like two fractions and just do a power rule? No, because you only have one term on top and two on the bottom, right? If that were flipped over, you could do it, right? So now you try this next technique that I'm trying to show you here today of U substitution. And so you're going to look for something, and you're going to try and find, is its derivative there also somewhere? And it's okay to be off by a constant. So do you see something and its derivative there somewhere? So what? Say it again, I didn't hear you.
3x squared and the x cubed.
Okay, the 3x squared and the x cubed, what about them?
The 3x squared is the derivative of the x.
Okay, so the 3x squared is the derivative of x cubed, isn't it? So I said you're going to try and find something that's going to be your u, and then its derivative needs to be there somewhere also. So the u will be the part that the x cubed. The u will be the thing before the derivative. So do we all agree that we could let u be x cubed? Yes? Yes? And the derivative of that is up here, isn't it? But could I even go further and use the +1 also?
Surely, yeah.
I could do that because the derivative of that is still 3x squared.
Yeah.
So x cubed would have worked, but it would have added one additional step to the problem. Here, if I grab the 1 also, I've got, it's kind of like this balancing act of grabbing enough, but not too much, because if you go too much, then the derivative gets ugly, and
You can do that with any constant that won't become a derivative. Right?
that's right. Yep. So let's do this now. We're going to go derivative both sides, du dx equals 3x squared, right? Now up here, I want you to realize that what you're looking at up here, you have to be willing to play with these, do some algebra here. I need you to realize that what you're seeing up here is actually this. That the 3x squared up top can really be popped out the side like this next to it as a fraction. Do you all agree? So now I'm playing this little matching game. I've got x cubed plus 1. That's this, right? That's going to be replaced with u. But now I need to somehow get rid of this junk right here, 3x squared dx. Well, I still need to multiply both sides here by dx. And do you see I have it exactly? Like 3x squared dx is exactly there. It's because I made the problem work out that way. Okay, so it's exactly there, isn't it? I mean, 3x squared dx came from here. That is exactly what I have here. So what will I replace this with? du. And I'm going to replace that with u. So let's do it. So this becomes integral 1 over u du. 1 over u du.
You cancel?
And no, that's du, not u. What's the antiderivative of 1 over u? What is the antiderivative of 1 over x? Natural log, right? That was that special case. So this is equal to natural log of u plus a constant. And now replace u. What was u? X cubed plus 1. So natural log of x cubed plus 1 plus c. That should be the answer. How do we check it? Take its derivative. So if I took derivative of that, derivative of natural log of something is 1 over, that's something, times the derivative of what's inside, which is 3x squared. And you pop that 3x squared back up here, and you get the integrand, don't you? All right, I think we have another one in order here. I have time. Now look, you could take that x to the fourth minus 5, and you could do it times itself 7 times, and then pass an x cubed through and avoid doing anything else. But I changed that to a power 70, and then I think I can make you submit, right? So let's see if we can't do substitution. What's that, even 7? Even 7, yeah. So what do you think? Do you see something that you can pick for u, and then its derivative also, but it's okay to be off by a constant? So look, x to the fourth? Minus 5. Let's go for that. Now, I always tell my Cal 2 students when they're learning substitution, you have to be willing to take a swing, okay? You have to be willing to try something for you. And if it doesn't work, it doesn't work. Be prepared to fail more times than you succeed. For sure, in Cal 2, you will fail more times than you succeed when it comes to trying to integrate. All right, but you have to try something. You have to try something. Okay, you can't just be like, I don't know, I'm just going to go to the tutoring lab. All right, so this is u. Now, you picked this, I think, because you see that its derivative would be 4x cubed. And you do see an x cubed out here, you just don't see the 4. But it's okay to be off by 4. So thinking a little bit ahead of where I'm headed with this, I'm going to peel that x cubed back to the back with the dx. Like this piece right here, I'm going to try and get rid of. This is going to be a u to the 7th at some point, right? U to the 7th? But it's that x cubed dx. How can I resolve that? So let's go over here. Du dx is 4x cubed. And then multiply both sides by dx. That step right here, multiplying both sides by dx, you pretty much will do every single time. Every single time I will do this. So from this point forward, I'm going to go straight from here to here. I'm no longer going to multiply both sides by dx. I'm just going to go from here to here. All right? It just saves us time. Okay, I'm trying to replace x cubed dx, right? Over here, I have 4x cubed dx. So I can just divide both sides by 4 again. This will become 1/4 du is x cubed dx. Yeah? Yeah. Now, it's just plug and play time now. So this is going to become, this piece right here is u, right? So u to the 7th times x cubed dx, which is 1/4 du. And that 1/4 is just going to come for the ride, yes? And because it comes for the ride, we do actually get to a point where we start bringing all constants outside of the integral sign, like that. We just start pulling all our constants out. I haven't done that yet. I've always left them inside, but this is multiplication, so it can just come out. Now, the important thing is you can pull constants out. You may not pull variables out. So you can't like pull anything with a u out, or else you're breaking rules. That's like if you pulled, I haven't shown you this, huh? Okay. This is 1/4. I haven't shown you one of the most beautiful things. Can't believe it. Can't believe myself. All right, this is it. 1/32 u to the 8th. What's u? I erased it. It was x to the 4th minus 5, right? To the 8th plus c. And you could check that by taking its derivative. And after you do the chain rule appropriately, 8 will come out, the power will come down to 7. Derivative of the inside is 4x cubed. The 4 and something will cancel. And at the end of the day, you should get this. Questions? Okay, so now I told you I forgot to show you something beautiful. Do you remember? You don't need to write this down, okay? Do you remember I had this on the board though earlier? Okay, I had this on the board earlier. I used delta x here instead, but delta x was b minus a over n. This is the true area underneath the curve, right? I wanted to talk a little bit about where this notation comes from. All right, this is the same. If you want to do this, this would be the same as this. Right? You can do that, or you can do this, right? So let's see where things come from here. This piece right here was delta x, right? If I let n go to infinity, this becomes almost like 0, right? Because it's a width. It becomes like infinitesimally narrow, yes? Okay, that is this part of the formula. It's the delta x with n going to infinity is this piece, all right? This f right here, this function is this piece right here. Okay, can you kind of see it? It's like f of x, there's some number in here. F of x, width of the rectangle, so height times width, right? And this symbol right here, the integral symbol, comes from the idea of taking the limit of a summation. You're taking the limit of a summation, so that's why we use this capital, like stretched out S. That's what the symbol is, like an elongated S. And it represents the limit of the sum, if that makes sense. So do you kind of see where the two notations come together?
They're kind of the same.
They are. But I mean, if I just, like when I come up here and I say, hey everyone, we use this symbol for antiderivative, like if you've never seen a Riemann sum, like you have no idea why we're using that symbol. We're using that symbol because it represents a summation, but not just any summation, it's the limit of the summation. Make sense?
Yes.
Okay.
So the limit's represented by the outer letters, and then the summation's represented by the S, right?
The limit is represented
And
by,
the B and the A, that represents the limiting part, right?
okay, yeah, you could say that if you, yeah. Okay, I think we should try one more before we go. I like this next one. This doesn't mean I'm going to test you on it. This just is very cool what happens here. All right. Do you see something in its derivative? X plus 1? And what's its derivative? 1? And there's a 1 there, isn't there? Yes?
Yeah.
I mean, there's a 1 anywhere, right? You say there's a 1 here. I would agree, x plus 1 and its derivative is there also. But that would have worked with almost anything. Like you could have said, for any of these problems, you could have said, let u be x.
Yeah.
And its derivative would have always been there, right? X plus 1 would also work. What I'm trying to get you to see with this one is that it doesn't seem like a substitution is going to make much of a difference here. Like it would be really nice if that were x squared plus 1. Let's just think about that. If that was x squared plus 1, what would its derivative be? 2x, and do you see a 2x? Well, you see x, don't you? And you'd be off by 2? And so that would work out real nice, wouldn't it? Do y'all see that? But without that being a squared, then I could pick that as my u, but then its derivative is 1, so then what about this? That's not u anymore, right? I mean, that's u, so I can't say that's u. So how do I, you see there's kind of a little bit of an issue here? And I sure as heck don't want to expand x plus 1 30 times. So sometimes you just, like I said, have to take a swing. Let's go with that first instinctive guess at x plus 1. What's du? What's the derivative of x? 1. And then notice I brought the dx to the other side already. Okay? I really don't need this 1 here, do I? No, okay. I'm going to be able to replace this dx with what? Du, right? So I've got that covered. I'm going to be able to replace the x plus 1 with u, right? But if I'm going to do a substitution, all x's must become some form of u. You can't have u's and x's mixed up. So I need to also be able to replace this x. But I don't have anything for x, not exactly. What could I do though? Why don't we do that? Why don't we take this equation and just solve it for x? Isn't that the same thing? If I'm saying that u is x plus 1, then that means that u minus 1 is x. Now, does that help us? Let's see. If I rewrite the integral, what does that x become? U minus 1. I'm put that in parentheses. And then what does the x plus 1 become? U to the 30th. And then dx becomes just 1 du or du, right? So did that help us at all, or did that just like make the problem look different but still ugly?
Different but still ugly.
Yeah? What was wrong with this? We couldn't do this one because I did not want to expand x plus 1 30 times, right?
Yeah, that's true. I see what you got here.
How about here, though? No expansion necessary. I can just pass this u right in. Here, I can't put that x in. Why?
Because it's
Order of operations, right? Exponents come before multiplication. So I can't push that x in. But here, I can pop that u through the parenthesis.
Yeah.
And if I do that, I get integral u to the 30th minus u to the 31st minus u to the 30th du. And then I can do each one of those with power rule. So that becomes, antiderivative now is 1 over 32 u to the 32 minus 1 over 31 u to the 31 plus c. And then replace your u's with x plus 1. So 1 over 32 x plus 1 to the 32 minus 1 over 31 x plus 1 to the 31 plus c. That's your antiderivative. That was an example. I showed you that because I wanted you to see an example where when you made the substitution, it wasn't real clear that it was going to work. But it wound up, because of this step right here, it wound up turning it into something you could do. Is that really the answer? I don't believe that that's the answer. Is that really? How could I check it? Derivative. Okay, real quick. 32 comes out, cancels. I have this to the 31. Okay, minus. Now, 31 comes out, cancels. I get this to the 30th. How in the world are those this? That doesn't, is that? Okay, so both of these have an x plus 1 to the 30th in them, don't they? They both do. So I pull that out, and then what would I still be left with there? X plus 1, and then minus, what do I pull them all out here, so I'm still left with a 1 here, and 1, these cancel, and you get x plus 1 to the 30th times x, which is this. It works. See, that's the good news in Cal 2. You can always check your work. But, okay, so I would say for homework, if you're looking, because there will be something on the final with substitution. No Riemann sums. Substitution starts on 5.5. So what I would do with 5.5 is I would try and do numbers 1 through 6 by next class. And here's the great thing about numbers 1 through 6. They give you the integral, and they give you the substitution. They say, let u be this. And that gets you kind of like going, you know? They get you started. And then after that, if you want to start exploring problems 7 through 36, those are just integrals and they don't give you anything. You have to find the substitution on your own. All right? So there is no such thing as doing too many problems out of that section. I would encourage you, by the time you get, into Cal 2, I would encourage you to try and finish 1 through 36. Because you'll be really off to a good step in Cal 2 if you can do substitution real well. All right? We will come back, talk a little more about substitution, and then maybe a little bit about the final. Let me turn off my camera. Is that the sun? I heard the sun wasn't coming out today.